Good morning, everyone. Let me welcome you to the 8th class of our crash course on data analytics for students of social sciences and humanities. Today's topic is machine learning, or better to say introduction to machine learning, simply tutorial on machine learning. And I'm aware that today's lecture is more formal than the previous ones. So please don't hesitate to interrupt me every time you feel you are getting lost. I will start with a formal definition of machine learning formulated by Tom Mitchell in 1997. And this definition says, a computer program is set to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Let me paraphrase it a little bit. So it says that a machine learning problem is defined by an automatic program, an automatic procedure that learns from some experience. I will specify what does it mean, experience, in this context, with respect to a task, to some task. In other words, a given software or procedure is addressing some task, and for sure, we want to evaluate this task. So we want to measure success using some performance measure. And idea is that the more experience a given automatic procedure has, then the performance is increasing. Let me illustrate this definition on the task of spam filtering. In other words, we classify emails. We classify an email whether it is a spam or whether it's not a spam. Experience is, for example, if you are using Gmail, you can report a spam. There is if you read an email or a message, there is a pictogram, this exclamation, and using it, you can report a spam. In other words, you classify messages in your inbox so that you are saying it is a spam, it is a spam. And we measure performance as using a measure saying or counting the fraction of emails classified correctly. So experience has a form of examples of spams and non-spams. But what does that actually mean? The definition doesn't really tell us how it is done in practice. So I will explain an idea of machine learning, of experience, of performance in details. You are already familiar with the systems UDPipe and NameTag. NameTag UDPipe is an automatic procedure for syntactic analysis, and NameTag detects name entities in the text and classify them into categories. And these two systems are examples of the systems of natural language processing. Let me characterize natural language processing as a part of the field of computational linguistics. Computational linguistics is a multidisciplinary study of human language in the center of the circle from a computational perspective. And it has two components, linguistics and computer science. computer science models language use, and linguistics studies language structure. And exactly this component, modeling language use, it is a natural language processing. In other words, we say that natural language processing deals with human-machine communication or interaction in both written and spoken natural language. And systems of natural language processing use corpora of text and speeches, sometimes enriched with linguistic information. In other words, they use annotated corpora or other linguistic resources, and I introduced you some of them last week. In comparison to mathematics and physics, computational linguistics is still a young lady. Its origin date back to the 1950s, when the very first experiments of machine translation, in other words, translation from one language into another using a computer, were performed. The results of those rule-based systems were not as correct as expected. To move this strategy forward, Professor Jelinek and his team at IBM approached this problem from a completely different perspective. At the end of the 1980s or at the beginning of 1990s, they introduced a statistical approach to machine translation. And it was so different for reviewers, it was so different that reviewers called it simply beyond the scope of computational linguistics at that time. And I think that it's very interesting to read a part of the rejection review. It was presented in 2009 when Professor Fred Jelinek was awarded with the ACL Lifetime Achievement Award. The validity of a statistical approach to machine translation has indeed been recognized, as the author mentioned, by Weaver as early as 1949, and was universally recognized as mistaken by 1950. And the crude force of computers is not science. The paper is simply beyond the scope of calling. An anonymous calling reviewer in 1990 said in 1988. Time has shown how wrong they were, and what more, it has proved that the interaction among scientists from both humanities and natural sciences is more than necessary. And this statistical learning revolution caused the great development of corpora, collections of text, and the use of machine learning. Part-of-speech labeling is an example of an NLP task, and the automatic procedure performing part-of-speech class labeling, tagging, in other words, is typically a module in almost every system working with natural language. Part-of-speech class labeling, it means that we assign a part-of-speech class to each word in a text. I illustrated on the sentence time flies like an arrow. Type is a noun, flies verb, like preposition and article, arrow noun. But for sure, words can have more than one part-of-speech classes. Another meaning of this sentence saying that flies, flies, a common small insect with wings, like an arrow. So in this reading, in this meaning, time is adjective, flies is a noun, or flies nouns, like verb, and this is the same as in the sentence. So words can have more than one part of speech classes, so that in the task of tagging, we disambiguate part of speech classes that are relevant to a given word. Now let me explain you a basic idea of machine learning approach, and I will illustrate it on the task of part of speech labeling. In other words, our task is to teach machines, computers, assign part of speech classes to words in text. First, let's think about part of speech classes, morphological categories relevant to these classes, and values of the morphological categories. Let's work with 10 classes, part of speech classes: nouns, adjectives, pronouns, verbs, numbers, adverbs, prepositions, conjunctions, particles, interjections. And we can work with categories like gender, masculine, and its value masculine, feminine, neutral, or with number, singular, plural. For Czech, we can work with case category, so the nominative, genitive, and so on, persons, first, second, and third. Then, in the step 2, let's design a tag set. For sure, we can use words to describe part of speech classes and values of morphological categories, but for automatic processing, it's definitely useful to use a tag set. Here I design a very simple tag set, positional one with 3 positions. The first position is for part of speech class, the second position is for number, and the third position is for tense. Then in the step 3, let's create an exercise book. In other words, we create examples. And in this task, in the task of part of speech labeling, let's manually annotate as many tags as possible. In other words, we go word by word and we assign 3 position tag to each word. Nadal plays with control aggression. Nadal is a noun in singular number, and tense, it is a morphological category not relevant to nouns. So this third position is empty, simply. Plays, it's a verb, singular and present tense. With is a preposition, and it doesn't make sense to assign or the categories of number and tense are not relevant to prepositions. Control, adjective, singular, aggression, noun, and singular. Then let's convert this exercise book to frequency tables. In other words, to a format for further processing, or simply for machine learning. And namely, we create 2 frequency tables. The first one contains words occurring in the exercise book with their tags. And for each pair word tag, we compute its frequency in the exercise book. For example, word Nadal with tag NS and S occurs in the exercise book 10 times. Place, word place with this tag occurs 15 times. Control as a noun occurs in the exercise book 5 times, and control as a verb, plural, and present tense 13 times. And so on. So from the manually annotated text, we generate this frequency table. Then we create one more table, and here we work with so-called tag bigrams. Tag bigrams, and it is a sequence of 2 adjacent tags. So going back to our exercise book, we can see which tags follow which tags, and from this sequence we generate tag bigrams. And how to read this frequency table? In the exercise book, tag noun singular is followed by tag verb singular present 10 times. So we, let's say, make a step up. We leave the lexical information and we focus on sequences of tags. Definitely the number of tags is lower than the number of words. The second row says that the noun in singular followed by noun in plural occurs in the exercise book just once. You can think about an example to illustrate a sequence of nouns, singular and plural, and so on, so on. Verb followed by preposition 15 times, and preposition followed by noun in singular 8 times. In general, we can work with n-grams. It means that we work with a sequence of n and adjacent tags, but we don't have to focus on text only. We can work with words, we can work with letters, we can work with syllables, simply with n-grams. Okay, so now we have the exercise book. We have examples transformed into frequency tables. And now we have a new sentence saying Nadal plays tennis. And we are supposed to tag or to label each word in this sentence automatically. Using this model, this frequency table represents a model of part-of-speech labeling. Okay, so let's start with the first word, with the word Nadal, and let's look at this table with the word tag pairs. We can see that this word is present, and we can see that only once. So we assigned this tag to Nadal. Then let's move to the second word, place. We can see that the word place occur in this frequency table twice, with as a noun in plural. Sorry, there is an error. in plural, or as a verb singular present time. And we can see that they occur in the exercise book 15 times. Both of them occur 15 times in the exercise book. So we cannot say, we cannot assign a tag to the word place because of the same frequencies. So then let's look at this, the second part, or the second frequency table. Frequency table containing bigrams, bigrams and their frequencies. And we already know that the tag preceding this word is a noun in singular. So we check all the bigrams where the noun in singular occur in the first position. And there are two bigrams. This one is a bigram of noun, of noun and verb, and here is a bigram of noun, singular, noun, plural. And this bigram, this one, occurs 10 times in the exercise book, and this bigram only once. In other words, this bigram is a winner, and therefore we assign tag verb singular present to the word place based on the history, since we know since we already know the preceding tag. Okay, so now let's label the word tennis. Tennis doesn't occur in this frequency table, so let's check this table. And also, based on the context, we know that the preceding tag is a verb singular present, and there is only one bigram with this tag FSP in the first position. So we label the word tennis with the tag for preposition. And for sure it is an error. Tennis and preposition, it doesn't make sense. But it clearly illustrates the idea of statistical machine learning. In the exercise book, we have only a sample of sentences, and it can happen then it contains only a sample of sentences, and in a new sentence that we want to process automatically, they can occur words that don't occur in the exercise book. So we have to handle it somehow. It's not important right now to say details how to handle this situation, but that's statistical machine learning, right? So we don't work with a population of all the texts available. We have just sample. Are there any questions?
No.
No?
Thank you.
Okay, that's perfect. If there are no questions, so I'm happy to hear it. Okay, so and that's exactly machine learning, and namely so-called supervised machine learning. Supervised machine learning, or we can say learning by examples, or learning with teachers. So there is a teacher supervising the learning process, and we teachers, annotators, create examples and tell computers how to learn from them. In the task of part-of-speech labeling, we create examples of labeled or annotated words, and we say, let's learn, or not, we say computers learn from these examples using frequency tables. It is the using of frequency tables. It's very simple approach, but I think that it clearly explains an idea of machine learning. So now let me explain in machine learning terms and an idea of supervised machine learning in great details. At the very beginning, we have real world objects. In the task of part-of-speech labeling, words in text are real world objects. When working with Titanic dataset and when we predicting which passenger survives, we work with passengers on Titanic. Real world objects are passengers on Titanic. What to extract from examples, right? We have real world objects and we have to represent them so automatic procedures can work with real world objects. Simply we cannot upload I don't know, persons or flowers into computer. We have to represent them. And if we humans label part-of-speech, or we label words, we use our knowledge of grammar. We have a real world knowledge. We have some intuition, some reason. But computers don't have this information, and they have to extract a set of context clues that they use for addressing a given task. And formally, the context clues are called attributes or features. And they represent properties of real-world objects we are working with. And attributes, features, they have to be defined exactly and explicitly. And then we represent real-world objects using a so-called feature vector. So we describe real-world objects with a set of features. For example, if we use, I don't know, 5 features, so then each real-world object is represented as a vector of 5 values. The properties we use, or the properties of objects we are working with, we can observe them or measure them, and they can be of several types: numerical, continuous or discrete, then binary, means that there are two just two possible values of a given feature. And we use notation zero. We use notation 0, 1, or true, false, or yes, no for binary values. And
I have a question.
yes.
Okay, so when I was studying logic at the university, we were going through the topic of pair-consistent logic, where the value of a statement can be not binary 0 1, it can also in 1 and the statement can become either true or untrue, depending on which statement it is put next to. Is there something similar within interwoven into the features of machine learning? Because I know the field of consistent logic is relatively new. I was just curious, but it also and in this collocation, the word is an adjective, but if the value is adjective, right? And if we put it next to another one in a different position in the sentence, then the computer should be able to define it as a noun. So I'm just kind of trying to connect things that I already have in my brain with what you're saying right now.
I do understand your question, and let me finish this description, and then I will provide you with some examples. And I think, and I am sure that then it will be more clear what we mean by true or false binary examples, right? So the binary features. They represent a special case of categorical features. And categorical features, it is a list of discrete values, non-numeric. Right? In the Titanic data set, here we have here we have a sample or subset of the complete data set, and this subset contains 10 feature vectors. Here, each row is a feature vector representing a passenger. And here we have a number of features or properties of the passengers, and one of them is sex. It is a binary feature. We observe there just two values, male and female. We can transform these values, male and female, into 0, 1 values. For example, if a passenger is female, then the value will be 1, and if it is a male, then the value is 0. Or using true and false words, true says, okay, this is a woman, and false, this is a man. Then here we have a feature called SIPS, and it stands for the number of siblings and partners, spouse, and it is a numerical discrete feature. Or here we observe numerical values, and definitely the maximum is up to 10, and so we can list the values of this feature. So numerical discrete. On the other hand, there is a feature fair, and it is a numerical continuous. It's hard to list the values. We observe real numbers. real numbers, the values. And here, embarked, it stands for, it is a categorical feature with 3 possible values, C, S, C, and Q. And since there were 3 ports of embarkment. So here is the illustration of features or of feature types we are working with. And each real-world object, passenger on the Titanic, is represented as a feature vector. Sophie, did I answer your question?
Yes, kind of. Okay, maybe I'll listen more, and then maybe I'll be able to formulate my question better, because I think I still have like some questions left, but I want to see if, like, how it progresses, because I feel now I need more time.
Okay.
Better.
Okay. So I will present a supervised machine learning as a triangle, and now we know this now. So we are speaking about real world objects, and we have to represent them, and we use features, and then we represent each real world object as a feature vector. That's what we just did. And working with M features in general, we have a vector of M values. Going back to part-of-speech labeling, words in text are real-world objects, and we can use features, for example, preceding word, preceding part-of-speech tag, word ending, and so on. All these 3 features are categorical ones. There are a list of categories. Okay, so this part of triangle concerns the data and data representation. And this part, or namely this node, concerns a task we are supposed to do. We do predictions. We predict some property of objects. So, for example, for part-of-speech labeling, we classify each word into a class described using part-of-speech text. So for example, for sure, we can use just part-of-speech class, just one feature or property of words. We don't have to focus on morphological categories. So then we classify words into 10 classes, each of them corresponding to one part-of-speech class. Or in the Titanic data, here we read target values. So our task is to predict whether a passenger survives or not. There are 2 target values, 0 and 1, or yes and no. So the target values are categorical ones, and here is the special case, binary ones, only 2 possible or 2 target values, in comparison to 10 target values for part-of-speech labeling.
I have a question in regards to the survived and the binary categorization there. What if we want to say survived, deceased, or undefined? Like, if this person is like missing, and if we like cross-reference the data from this table to another data, like from an additional source, can we like make the computer sort out the undefined passengers in the in the process of cross-referencing another data about the deceased and survived passengers?
Then we have to create more examples. Here we read examples working with just two values, survive or not survive. And to work with more values, we have to prepare new examples. So using machine learning, we teach computers to learn knowledge present in the data. So if we have data in this form or working with two values, there is no way how to learn another value. Does it make sense?
Yeah.
Or we can predict numerical property. I'm very sorry that I don't present you an example from Humanities, but here is just example. Then we work with cars, real world objects, and for each car we predict miles per gallon that a given car passes. So miles per gallon is an example of a numerical attribute or numerical property. And based on a type of a target values, we distinguish classification and regression. If target values are categorical, then we speak about classification. And if target values are numerical, we speak about regression. This image on the left, each example is described using two features, A1 and A2. So each real-world object is represented as a vector of the length 2. And we do classification in two classes, 0, 1, or red, blue. A target value is categorical one. Here we work with cars, and we work with just one feature, namely with the feature weight. And based on the value of this feature, we predict miles per gallon. So these blue points visualize examples, regression and classification. Okay, so let's back to a triangle. And now we do understand what the nodes, real-world objects, feature vectors, and target values stand for. Here we do data representation, and what we are doing here, going from real-world objects to target values. We do so-called true prediction. In other words, we create examples that we call gold data. So in the task of part-to-speech labeling, we annotate words in text. We read word by word and label it with a part-to-speech class. So we do true prediction and we prepare examples, gold data. When I presented you a basic idea of machine learning, I speak about the gold, or I called gold data as an exercise book. Or if you are, for example, getting ready for some exam, so you read books, or you read exercise books. So that's the reason why I use this term exercise book when presenting you a basic idea of machine learning. But gold data, that is a term from machine learning, and it stands for examples. So in part-of-speech labeling, gold data is a set of sentences or tags where each word is assigned with a part-of-speech tag. Okay, so that's what teachers, speaking about supervised machine learning, learning with teachers, that's what teachers do. They prepare or they create examples. But in an automatic procedure, we are here between these two nodes, between feature vectors and target values. We don't know a true target function between feature vectors and target values. We don't know what is a function, that a true function that map feature vectors to target values. Therefore, we have to approximate it. So we have to approximate it, and we approximate a true target function using examples and machine learning methods. And then we get predictor, which is an approximation of a true target function. And this image illustrates an idea of a supervised machine learning. We prepare gold data, and using machine learning method, we approximate a true target function. When I explain you how we can teach computers to do part-of-speech labeling, I used a frequency table. It is one form how to approximate a true target function. Very simple representation of a function, mapping feature vectors to target values. We can characterize a machine learning process as a 5-step procedure. We start with formulating the task, to specify real-world objects, to specify target values and their types. Then we have to get examples, gold data, and we split them into training and test subset. Using training, we train a model and we test it on test data. Going back to the sample example, test subset was a sentence, Nadal plays tennis. So we trained frequency tables from the examples, and we test them on a new sentence. And step 3, we learn from training examples using machine algorithms, and we get model or predictor. model, it is a theoretical term, and predictor is a practical term. And then let's test the learned knowledge on test examples to evaluate this predictor, this automatic procedure. And finally, step 5 is the evaluation. Let me go back to the very beginning, or to the formal definition of machine learning. So now we can see that experience means examples, task is some task, and performance measure is the evaluation. And I'm presenting you an idea of statistical machine learning, and the statistical. So we need we are working with the sample of population, but the more data we have, the more the more examples we have, the better. In other words, the performance of predictor is getting better and better as we have more and more examples. And that's exactly what is said here. If its performance improves with experience, right? Experience with more examples, the performance is higher and higher. So 5-step machine learning process, and I'll give you an example of machine learning algorithm. It is a decision tree algorithm. It is a traditional supervised machine learning algorithm, and decision trees represent these functions. So we use a structure of decision trees as a representation of this target function. Decision tree. So it means that we use a data structure tree, and decision, it means that we have to do some decisions. Here is an example of a decision tree. So how to read it. This tree, here is the, it contains nodes and decisions. This node is called a root node, and here are the branches. So it is so if you look at tree, it is the opposite orientation. Here we have a root and branches. So here is the root node, and these nodes are internal nodes. These blue and green nodes are leaf nodes with target class values. This is a decision tree trained on Titanic data. Therefore, we work with 2 target values, 0 and 1. And decisions. Each internal node, including the root node, is associated with decision. At the root node, decision is, we ask whether a sex, whether the value of this feature is male. If yes, then go this direction, and if no, go this direction. Here we ask whether the passenger is older than 14, And if yes, we say 0. So we predict that this passenger will not survive. In this direction, if it is a child, then we ask what is the number of his or her siblings. If the number is higher or equal to 3, then we say yes, this passenger will survive. Otherwise, we say 0.
Recording in progress.
I'm sorry? I cannot hear you. Well. What was the question?
It wasn't a question, like
it was a noise.
Yeah.
Noise in the background. Yeah, so this is a decision tree. This is a model trained from the examples and using decision tree learning algorithm. And these decisions are binary questions, so there are 2 possible answers, yes and no. And so it means that each node has just two child nodes. And so two branches go from each internal node. So it is, as I said, it is a traditional machine learning algorithm, and its visualization is clear. So I think that everyone can get an idea what's going on. Okay, and now, so we trained a model, and let's test it on test data. This table, we call this table confusion matrix, and we apply this procedure or this decision tree to do prediction on test examples. 98 plus 20 plus 13 plus 47 is the number of test examples. And in columns, we read the prediction, and in rows, we read true values. So we can end on diagonal, we read the number of correctly classified examples. So 98 passengers which survived being 0 were classified into class 0, and 47 passengers positive were classified into class 1. And of diagonal, we read the number of misclassified examples. So 20 negative examples were classified as positive examples. Right? So 20 passengers that didn't survive were classified as a survivor. And confusion matrix is a table that we use to evaluate binary classifiers. In other words, we classify examples into two classes. And spending 2 years with COVID-19, I think that almost everyone is familiar with test sensitivity. What does it mean? And it comes from this confusion matrix, where we know what was the prediction, whether positive or negative, and whether it was correct or incorrect. And using this confusion matrix, we define a number of performance measures. And one of them is sensitivity, that quantify an ability of a classifier to correctly identify positive examples. In other words, to correctly identify survivors or patients with disease. generalization. So we know what's the practice of machine learning with data representation and target function and mapping of feature vectors to target values. And we learn by examples. We are training from training examples, and then we apply a model or predictor on unseen data, on test data, on data that were not included into training data. And generalization is ability of model or predictor to generalize beyond training data. And because during the learning model or predictor, we are trying to fit training examples. But we cannot overfit, because then the generalization will not be as good as we expect. So generalization is it's an idea of machine learning approaches. Okay, so that's all about basic terms of machine learning. Do you have any questions? Would you like to ask, or should I get back to some terms or ideas?
I don't have any questions.
Perfect. Perfect. So now I would like to present you homework number 5. Subject labeling in an EU regulation. And here is a web page. I hope that you can see the web page. Yes or no, 0 or 1?
Yes.
Yes, perfect. So subject annotation. Yeah, so it is the annotation task, and we will be preparing gold data. Gold data. And annotation task is that annotate subjects in the sentences of the preamble of the EU regulation. So we have a text with sentences, and each sentence we are supposed to annotate subjects. Subject, syntactic subjects and predicates to main dependency relations in sentences, and we are focusing just on subjects. And our motivation to organize this task is twofold. So first, as I already said, we want to prepare gold data, and so that we evaluate the UD pipe system for syntactic annotation on this data set. So manually annotated examples, and we can use them to evaluate UD pipe system. Also, we can check the inter-annotator agreement, because this EU regulation is presented in all 27 languages of the European Union, and so we created folders for each of you, And since the group of Czech students is the largest one in the audience, so then the Czech version of this regulation will be annotated at least twice. Right? So then we can compare the agreement between annotators. And the second motivation is that you should get, or it is an opportunity to get experience with readability of legal text. In 3 weeks, we will be speaking about readability of legal text. So we think that the practical experience will be useful. To understand well what we are speaking about. And so this is the motivation to organize this annotation task. Here is an example of the sentence from this regulation, and it says, once a candidate country becomes a member state, it joins a legal structure that is based on the fundamental premise, So here we can see 3 subjects: country, it, and that. We will use an annotation editor called BRAT. If you remember, I mentioned it at the very first lecture, and when I was speaking about the annotation of attribution. So having newspaper articles, and we are interested in sources the authors attribute to. So we are working on examples, and we use BRAT editor to annotate the examples. After this lecture, you will get an email with the instructions, and also with the link to BRAT editor. Is a web-based editor, so you don't have to install any annotation tool. You can simply work in your browser, and link to your document will be listed in the email. So your task is to read carefully the document and identify subjects in each sentence. You can be confused a little bit why I, here in this sentence, why I annotated country only as a subject, only a country as a subject. Why I didn't annotate it candidate country, this entity. We, in the instructions or in this task, we follow the principles of the universal dependencies annotation. You are already familiar with this framework of syntactic annotation, universal dependencies. And in this framework, the basic units of annotation are words, which means that the subject is exactly one word in our annotation task. And typically it is a noun, country, pronoun, it, here in this sentence is, or that, or relative pronoun, that. So let me open BRAT. Login. So the login name and password you will get them via email. Right. With my keyboard. Oh yeah. So now I signed in, and here is the English version of the preamble of the given regulation. I annotated these sentences. The first, it's not. I cannot explain you why, for example, this number 6 is missing, or number 9 is missing, 12 is missing, but definitely the preamble is complete. So we don't have to care that this that there are some numbers missing. So let's start here in this with the first sentence and read it. So the union is founded on the values. So union is a subject in this sentence, as recalled by those values are common. So value is a subject. Are common to the member states in a society in which pluralism, non-discrimination, tolerance, justice, solidarity, and equality between women and men prevail. Here is the coordination of subjects, coordination structure, and the instruction says that annotate each subject or each member of coordination separately. So therefore we separately annotate pluralism, non-discrimination, and so on, so on. Now I want to illustrate you the annotation process, how to mark a word and how to delete the annotation. Okay, so let's read this this item. So the laws and practices of member states should continue to comply with the common values on which the union is founded. So tell me which words are subjects in this sentence.
The laws and practices of
Yeah. So here is the coordination, laws of member states and practices of member states, and subject should be just one word. So laws is the subject. So I double click on this word, and you can press enter or OK. Then practices, again, double click, OK. Should continue to comply with the common values on which the union is funded. Union is subject. I would say that the marking the subjects is intuitive, and you don't have to be afraid of any troubles. And for example, if let's just for illustration how to delete an annotation. So let me mark this word as a subject, okay? And then I realize that I am wrong. So again, I double click on this word, and here I press this button, delete. And this is a way how to delete an annotation. Are you sure you want to delete this annotation? Okay. And it's removed. Okay, so this is so we are using annotation tool, BRAT annotation tool, new annotation, mark a subject with the mouse or with double click, or you can double click, or you can simply use mouse to select the word. So there are two ways how to how to mark the word. So I will add double click to this. I will add double click here, and how to delete the annotation. For sure, don't hesitate to send us an email if you are not sure whether you are doing well or if you deal some technical troubles. We will send you an email with answer, but we will also post your questions and answers to this web page as well. You can when you start annotating, you can see these two messages. Please ignore them. And I am not sure. I would say that if they appear only once at the very first attempt to, or at the moment when you open Brad for the first time. So ignore these error messages, and it can happen that the pop annotation window, this window is too high to fit your screen, so that you, especially when you are removing annotation, you simply have to see this button to delete the annotation. And it can happen that this pop-up annotation window is too high, so you cannot see this button. So please use Ctrl+ or Ctrl- to resize this annotation window. It can happen, especially if you are using laptops, so small screen. So then this window could be too high, so you cannot see this delete button. Yeah. Oh, if you don't see the button OK or delete, control the size of web page using Ctrl+ or Ctrl-. Do you have questions?
No.
No? You have 2 weeks to finish this annotation task. So due date is April 19. April 19, and you don't have to save the data. You simply just annotate the data. Your annotation is being automatically saved, so you can get back to it anytime, and you can edit your annotation. So in this case, just to delete them or edit them, and no other action is required. Here in the menu, if you check collection, and if I browse the structure, the folder structure, so you can see that the document, the preamble, is presented its Czech version, German version, English version, French version, and Polish version. And based on your language preferences, you filled in the survey at the beginning of the course. So we assign you the versions based on this, on your answers. And if you are not fine with the language we assigned you, for sure we can change it. Just let us know. So, for example, for Czech version, There are 5 folders, and this one is for me, test one, and these are for Czech students.
I have a question.
Mm-hmm.
Do we have to send you an email when we're done, or will you just check the Brad tool?
You don't have to send an email to us, but for sure you can, and we appreciate it. But we can check the documents, and we can see how many sentences are already annotated or not. So you don't have to send an email.
Okay, thank you very much.
Here we can see that the Czech version will be annotated at least 4 times. So there is enough data to measure inter-annotator agreement, to see how annotators understand the task and how they understand the instructions. It will be definitely very interesting. German version, English version, French version, Polish version. Here we immediately see the number of subjects annotated. So at the very beginning, there is 0, but once you create more and more annotations, this number is getting non-zero. Yeah, so as I said, we will send out the emails after this lecture in the afternoon. If you don't get an email by midnight, please let us know. Very recently, we organized the attribution annotation task, and we sent an email to more than 200 students, and it worked perfectly. So I don't expect any troubles, but for sure it can happen. Please let us know if you don't get an email by